And we're live. Hi, everybody. This is Justine Diamond for the Naval Community Foundation, and we're here to do a intern roundtable with our interns for the 2016 program. And I think I am going to put Jessica on the spot and start with her today because this time we get to see her. She had some camera issues last time. So, hi, Jessica. How are you?
I'm good. So
Good.
yeah, last time I had the camera issues, so I made another PowerPoint because I had a feeling that wasn't going to work again. So I'll do a screen share and update you guys on what I've been working on. Okay, can everybody see this?
Yep.
Okay. Yeah, so this week I was basically working on the forearm design. So to update everyone, I've been doing the playful prosthetic, and I basically put that into 3 different sections. So you've got the forearm design, which goes over the residual, and then you've got a bicep design, which obviously goes on the bicep and is the connector between the elbow and the forearm. And then the third piece, which I've broken it into, is going to be the piece that has the attachment onto it. So I'm trying to take things piece by piece and just break them down one by one, and then obviously put them all together at the end. So this week it was the forearm designs, and it was a bunch of really out there things that we're trying to just get a feel for how things can be thermoformed. Because one of the main things about this design is that I want it to be able to be thermoformed. So something that's really difficult about that is that you're taking something that's flat and you want it to look cool and you want it to be functional, but it also has to fit in a really ergonomical way around someone's nub, basically, which they're all shaped very differently. And so it's been kind of difficult. So with these two designs, these two right here, I pretty much knew it wasn't going to be perfect just because how big the spiral is and how like round it is basically. So when you're taking this, which is flat, and you're trying to shape it around something, I knew it wasn't going to be perfect, but I just wanted to see what it was going to be like. So we've got this one design, which you can see in the center has just like the base, the circle here is just like a placeholder because it'd be a placeholder for where the attachment would go because I wanted to see how that was going to be thermoformed too and how moved out of shape it was going to be. And then this design was another one that I wanted to test in the center, where it's basically like a drill chuck. If you guys have ever used a drill. Oh, can you guys not hear me?
No, we can hear you. We had background noise, so I muted everybody.
Okay, okay.
So everybody just unmute if you need to say something. It just
Okay,
helps with the quality of the sound on the recording.
okay, gotcha. So yeah, so this piece in the center is going to be similar to a drill chuck where it's all threaded here, and then this piece on the inside is threaded also. And so you've got these 4 prongs basically, and so you can put anything that's like straight in. So if you have like a screwdriver or something, you can just place it right into there, put this piece around it, and the idea is that you can just twirl it down and just on the threads, and it'll get tighter as you go. Um, and so that was the initial idea. So basically I was thinking, well, I'm printing these 2 things already, these 2 different designs to see how they're going to be thermoformed. I might as well test the attachments pieces on them also. And so as you can see, the thermoforming was a little wonky. So we knew it was going to be like that for the most part. I just wanted to see to what degree it wouldn't work. And so this one, which had the threading on it, the threading worked initially for about 5 minutes, and then the tighter we went, and obviously the plastic and shells and infill and everything has a lot to do with this too, but you can see one of the prongs like broke off and snapped there. And so I think we're not going to be going down that alley. We're using the same drill check method because when you're using plastic and you're trying to get something really tight and you want a wide range to be able to put different dimensions in there, it's just not applicable. And then with the blue one, I still liked the idea of the blue one where it's got these arms coming down. And the reason I put the spirals around them was because I figured so you need these 2 arms because that's where it's going to attach to the elbow. And then these 2 arms were more for stability. But if you just had these 2 arms there and they're not attached to anything like these other arms, then I figured they'd just be getting in the way and kind of hitting the recipient's arm in weird places. So I want it to be attached. I just have to find a better design as to how it won't end up like this, where you have all this weird material coming out at different angles and just made it worse. But it also has to be aesthetically pleasing still. And so then after these 2 ones, I met up with Steven, and we decided to do a simple design, more simple like this. So this is just like a super intro that I printed. I made it in like 5 minutes and was like, okay, let me just see how this thing is going to be thermoformed. So the idea is that you'd have your PVC or whatever is going in here, and however it's going to be attached, it'll just be in this is a placeholder. And then you've got an L arm coming out, and the idea is that it can spiral around. So this one was only about maybe like 4 or 5 inches, so it's relatively short. And we want like a really tight spiral, I would think. And then the idea is that at the elbow, it'll come around a full 360 and wrap all the way around near an elbow point. And then you'd have 2 prongs coming out that will attach to the actual bicep joint. And so that one was sort of promising. But then when I was sitting down thinking about it, and I was thinking about how the unlimited arm and how the Raptor and Phoenix hands all do their thermoforming, because obviously this isn't the first time that this challenge has been taken over, basically, where people have had to think about these things before. So I thought maybe I should be piggybacking off of them. And so here you've got the Phoenix, I believe, and here is the unlimited arm. And so I don't know if you guys are super familiar with these. I'm sure Justine is, and a lot of people are, but the unlimited arm gets twisted, so you've got a 90-degree angle where the hand's coming out, and then it's obviously attaching right here to the elbow. And so it doesn't go, it's sort of the spiral design, but just to a lesser degree than what we were thinking. And so I think that's a good alternative too, because these 2 attachments here don't go around the full 360 degrees. It's more 180. So you've got one attachment at the wrist and the other attachment on the opposite end of the wrist. I think that might be a good attachment idea. And then maybe just trying a simple one, like similar to the Phoenix, where you just got like a parallelogram basically that's coming down, and it just gets wider as you go. So you can make it wider at the forearm. Let's see. And then one other idea that we encountered this week was instead of Velcro, and this has been used in the, I think the Cyborg Beast uses this, if I'm not mistaken, but it's called BOA technology, and they use it like on ski boots and ski jackets and stuff like that. But it's basically this wire that gets wrapped around. If you guys can see in here, there's a spool and a knob and a housing. And so I actually have one right here. But as you tighten it and this spool, it tightens it, and it's really super effective. And I thought it'd be more discreet than using Velcro because I could lace it through the actual plastic, and it'd be less cutting in. So let's see. How do I get off screen share?
It should be at the top of the screen. It should say stop sharing my screen. There you go.
Oh, okay, cool. Yeah, so I've got one right here. And you can buy them they come in ace bandages a lot and stuff that goes on your elbow. So as you just crank it, and you can hear the crank, it gets tighter, and then you can undo it, and it gets looser, and it just has little teeth on it. So I think that's a really good thing for us to use probably in the bicep area, and then maybe even going up into the forearm too. It depends how long the recipient's forearm needs to be. Yeah, so that's what I've got for this week.
Oh, wow. So, with the Phoenix thermoforming, the gauntlet for that, you just dip it in the water instead of putting it completely in the water so that you don't transform the shape of the dovetail, because if that gets did you have to do that same thing where you could only dipping part of that in when you were doing the thermoforming?
Yeah, that's what I did for this piece too. So this would kind of stay semi-flat, but I also wanted to see what would happen if I got it all the way in and how much is going to be deformed. But something that's really cool about the Phoenix hand that I've used, we use the reverse dovetail, and so it doesn't need, like you can dip the whole thing in, and it doesn't really matter what shape it goes into because it only uses one really, really small, like 1/4-inch piece to attach the brick, basically, what's it called?
Right, the tensioner block.
Yeah, but I like the simplicity of those designs more than these. I feel like we're getting kind of convoluted where it's like we're trying to get these really complicated designs when really it can be something that's quite simple and just does I guess, you know what I was talking about with the unlimited arm where it's like the palm is here and then it just kind of twists.
Yeah, you have to twist it.
Yeah, but it's a lesser degree of the spiral than we were thinking.
Yeah, once you've done it once and you see how to do it, it's not such a big deal. At first, it seems. I think it seems a little more. And then with the reverse, the current design of the reverse dovetail, the only issue I have with that is you can't do a fully functioning whipple tree without it being really high, the box being really big. So I know there's some work being done to try and change that so that you can use that because it's apparently a little more comfortable.
Yeah.
For the recipient. But I don't know how much of the functionality you lose by having a partial whipple tree instead of the fully balancing the load between the two sets of fingers.
Right. So for the end of this week, I'm basically trying to perfect this forearm design so I can have something like one out of the three pieces that I really like and is really functional and looks good and everything. So I'm trying to settle on one of these designs and really just go for it.
Excellent.
Can I throw something on the top of all of that?
Yeah.
And can you guys hear me? So
Yep.
Another issue that was brought up is when you have these as designs and you distribute them to parents or whoever to print them out, there's a large issue with scaling if you're going to have something on the end that can pop on and off. So if someone just blindly scaled up the CAD design, then the end piece, the paddle holder or whatever, won't be able to lock on to the connector. So the whole idea with taking a look at thermoforming as a way to customize rather than scaling up those CAD designs is one reason to do that, so that maybe we can distribute one design or a couple sizes of designs and they won't have to be modified too much by the end user at the design stage, and you can just thermoform and everything should fit together nicely. So that's also kind of the overarching goal from our side of things.
No, that makes sense. No, that makes sense.
Yeah, because one of the problems in the original Playful Prosthetic design, like the first one that we'd been using at Hand Camp, was that on the end of it, and it's all one piece attached, you're supposed to put a 1-inch PVC in, and so you've got this one entire piece that fits on a child's arm, so that has to be scaled correctly to the person's arm, and then the piece on the end that fits this uniform 1-inch PVC is also being scaled. And so we ran into that a lot, where it just take us an extremely long time to have to customize the.
Is there a way to make it parametric so that the part that needs to scale would scale, but the joint, that part would stay the same?
I'm not sure how to do it in SolidWorks. I know you can roll back things in SolidWorks, and so if everyone across the board was using the same modeling software as me, it'd be extremely easy. But I'm not sure how to do it in SolidWorks where that piece just stays exactly the same.
Okay.
I'm not sure if it's possible.
So there's an existing, I know for the Raptor Reloaded, there was an existing software online where you could basically you could parametricize the different parts. So you could say, like, just based on, like my client's dimensions, here's what it is, and it'll like maintain the key features. So like the pin sizes and like the screw size and things like that. It maintains those, but it keeps everything else scaled to the way that you want it to. And I think they use OpenSCAD. I've personally never used that before, but I know that you can do a lot of cool things with parametric design on OpenSCAD.
OpenSCAD.
That might be something, like if you're interested in
Yeah.
like looking more at it, that might be something to look into.
Yeah, because right now, like I said, we have it put into 3 different pieces, so we don't have to encounter that problem. But it'd be easier as far as like keeping things together and keeping them solid if I could do that.
Yeah.
Okay. I may have some other resources for you, Jessica. I'll take a look. Just it made me think of something, but before I rattle on about it, I want to just look and see what I've got before I send that send that over. Akil, do you it's Chris with you, right?
Yeah.
Yes.
Hi, how are you? Nice to meet you. I know
Good.
you were on a cruise last week.
Yes, I was not
Lucky,
here.
lucky. You were lucky.
Yeah.
Do you guys want to do your update?
Sure, yeah.
Yeah.
So over the past week, the 2 things that we've been working on was continuing printing the different hand like variations that we wanted to. So basically, as we talked about last week, there was a problem where the fingers would because the fingers on the hand are so flexible around this joint, the fingers would basically be flexing back. I can show it to you. Kind of like that, and so instead of holding on to an object, the object would basically push the finger joint away. And
Right.
so we tried a couple different things, and you can talk about that if you want.
Yeah, so we have sort of 2 main solutions to this problem, which stems from the fact that this joint right here isn't strong enough to withstand the backwards pressure of an object that you're trying to pick up. So the first thing that we tried was increasing the infill density of the hand and of the fingers, with the idea that it would generate more force when you try to pick something up because it's denser. One of the things we noticed with that is that if you go into the actual CAD files of these fingers, they don't have a lot of infill to begin with, and so increasing the density doesn't do a whole lot
On the hinges.
On the hinges,
Yeah.
right. On the hinges in terms of increasing strength. So what we're working on now, and what Akil did last week or the week before, was design a finger file for each of the fingers with a larger hinge. And so we just printed those out, and we are working on assembling a hand with them right now. But the idea is that the larger hinge, they're a little bit stiffer, and so they won't be pushed back as much when you try to pick something up. And then the next thing we're going to try from there is actually trying a different type of material that's a little bit less flexible than the Ninja Flex, which is what we're using right now. So we're going to use Semi-Flex, which is like the same thing. It's the same brand as Ninja Flex, just one step down in terms of flexibility. So we're going to test out all three of those hands and compare them to how the original works in terms of the ability to pick up an object.
So after like we have the different hands, like we're gonna want to test them out on something, and so I talked about like the rig, testing rig last week, and I talked about some of the technical difficulties I had with getting it to work. So now we have gotten to the point where we can get the motor moving. So I'll show you a video, and I'll explain how it works and what the purpose is. So screen share, okay. Give me a second. I don't know how these things work. Okay. This might be. I need to move it. Screen? I want to move into this one. That desktop. Okay. Now let's try it. Screen share. Yeah. Okay. Share. Okay. So can you guys see this video that I'm about to do? You can or cannot?
We can. Yes, we can.
Okay. Cool. Great. I'm gonna play it. Oh yeah. So, as you can see with this video, okay, so basically what's happening here is that there is this palm right here. So this is a paddle which will be inserted into the palm of the hand that like we want to test, and then by moving the palm back and forth, we can open and close the fingers. And so in its final form, we have a whole bunch of sensors around, and so basically those sensors can detect force, and then we can do cool things like calculating the force efficiency and figuring out like which hand designs are good and which hand designs are not that good. So I'm gonna pull up a schematic just to show you guys how it works. So I'm gonna screen share into a different. Hold on, give me a second.
That's fine.
Okay, so this one, right? We wanted to move this one into here.
You could just move like a couple of them.
Yeah, I mean, yeah, this is the only other one that we need. Okay. So with screen share, I'm gonna screen share this. Okay. Okay, so what we have going on here is this is a circuit design which explains how the force sensing works. So basically, you have this is like an op amp. So this is called an operational amplifier, and it takes a signal into the op amp, and then it basically magnifies it into a signal out. And so this is the same sort of like mechanism for how loudspeakers work and things like that. So what we have here is that you have like a 5-volt signal, which is going to come from like the Arduino, and I'm circling it right here. And that is basically being fed into this op amp, and then it's giving me a voltage out. And the cool thing is that the amount of amplification that the op amp does depends on this resistor right here. So this resistor called RS. And so what is happening with our force sensing mechanism is that the resistance RS changes based on how much force that we apply onto the sensor. So changing the sensor's resistance changes the amplification on the op amp, and so therefore will change the voltage coming out. and that's how we're able to detect how much force is being pressed onto this sensor right here. So that's the general mechanism for how it should work. Right now we're having a little bit of difficulties with figuring out like what components. Well, we're trying to figure out if something was misplugged, or we're trying to figure out if something's broken. And so to do that, we're going to run a positive control with just one sensor, one like input voltage, and then to basically assemble like one of these diagrams, because in the final design we have about 20 of these sensors that are being fed into a breadboard. So we're just going to try to simplify the problem into one, and then to see if we can get that to work, or if there's an intrinsic problem with how we're approaching this. So I'm going to stop sharing. Oh, okay, how do you get out of this? What if I close this? Okay, cool. So those are the major updates for this week and our goals for next week. Yeah, so if anyone has any comments, ideas, that would be appreciated.
I have a question for you. I'm just going to mute you while I'm talking because I got to go. Sorry about that. The hand that you're using, which hand is that? Because it doesn't look like the one that you were working on last year, and it's flexible, so I'm just curious. But you need to unmute.
Yeah, sure. So this is a hand this is a modified flexi hand that we modified last semester, and the whole idea is that it incorporates this natural wrist tenodesis, which means the idea that your power grip occurs when your hand is being flexed back. And so, like, for example, when you're holding onto a bike and things like that, you don't ride like this, right? You ride with your wrist flexed back. And so, and we talked to a doctor at who urged us to look into this possibility as a way to improve the hands. So how we modified the flexi hand was we basically made 5 channels on the bottom, and we ran some string, or in this case a tensioning string, to go from the fingers alongside the channels into the back where it's being tied onto the bottom.
Can you do me a favor? I know that if you normally when the hand bends, they close. Can you actually hold that one up and demonstrate the change that you guys have done so that the grip is the other way?
Sure. It's not completely all the way tensioned yet, but
we're still working on tension.
Oh, okay, that's fine.
When you flex it backwards.
Gotcha. Okay, that's cool.
As opposed to the other designs in which it's
right, it's that way, which is kind of uncomfortable if you have to hold on to anything for any period of time. It's very uncomfortable.
And it reduces the amount of force that you can generate total.
Okay, that's really cool.
Yeah, so that's
I'm very interested to watch that as that goes on. Okay, does anybody else have any questions for them? Jessica or Tricia? Oh, we lost Steven. That's okay. I'm sure he'll be back. Okay. Then we will move on to Tricia.
Can everybody hear me?
Yes, we can.
Okay, great. So as you mentioned earlier, Justine, we went to the Maker Faire here at DC just this last weekend, and Enable had a ton of traction, and it was really great because we installed a lot of the bars on the hand so people could actually put on the hand and flex them, try and pick up objects, and that was really great to be able to see because that gave me a good example. Even though people who had fully functioning limbs, bilateral limb function, it gave us a good opportunity to see just ordinary people trying to pick up the hands and use them, and we actually found a lot of the kids, as I'm sure you guys have all seen, the kids were really good at using the hands. They just picked them up and started like throwing balls, and it was really amazing. But a lot of the adults actually struggled, even though the hands fit them. The kids were just remarkably good at them. But we took a bunch of our hands to the Maker Faire, and so we saw a lot of different versions being used. We saw a lot of different things being done with the hands. And it was a good time to see kind of general weaknesses. The adaptive grip was really helpful, and so some people had preferences. Our Frozen themed hand has that Whipple tree inside, and so it's really hard to see, but it's in there. You can see the tensioner clip is a bit different, and so this seemed to be the hand that had done the best and had kind of the smoothest grip, had the best grip out of them. So I'm glad it was suggested to print and test a whipple tree. We are getting on that, and we'll be including that into some of our designs. But what we've come up in the meantime, we've done a few general tests as well. We're still narrowing down our testing protocol where we've kind of finalized a list of what we want to test and a bunch of the functional things we're looking to see whether or not the hands can actually do. But we've come up with some rough numbers. So the Phoenix hands, we tested some of the 1.3 sized Phoenix and Raptor reloaded hands. And again, both of them take about 13 newtons to become completely closed. So when you do pull back on this hand and get the hand to be fully flexed like this, this is about 13 newtons of force. Although this hand, we actually tested this one, and then we have another hand in the Raptor reloaded. The Phoenix hand uses that adaptive grip, and so we found that it only took about 6 newtons of force to hold objects, whereas the Raptor reloaded hand that we had tested was a little bit more difficult to pull, probably because of that black elastic in the back of it. Again, to keep it fully closed is about 13 newtons of force at the end. But the the Raptor reloaded hand could not hold on to objects like an empty tennis ball tube. It couldn't hold on to that, even though we were exerting about 13 newtons of force. The hands just could not grip. So we'll test it with those adaptive finger sleeves or fingertip sleeves. I don't know exactly what to call them. We'll put some of those on both of the versions of the hands and see if that will improve the grip function, which I expect it will help at least somewhat. But we definitely saw a difference in the Phoenix hand. It was able to grip objects better at lesser forces. So to maintain that grip on that empty tennis ball tube, we found that we only need about 6 or 7 newtons of force, depending on how we placed the tube in the hand. And that seemed vastly different than what we saw in the Raptor reloaded hand. So we've seen that. We're definitely keeping an eye out for nuances, for things that are going to be significant. But I definitely am a big fan of that adaptive grip, and so we'll just kind of see where that goes. We've also rewired a bunch of the hands, replaced a bunch of the bands, so we're getting everything ready to go for a full testing phase. But the hardest part is over because we have a pulley system that works. We've also designed a testing protocol, and it's this kind of strange-looking bit here, but what we did is we just put a blood pressure cuff fully assembled. We wrapped it around an object that's just the thing we had in our lab. We wrapped it around and secured it, and all we're doing is we just are inflating the blood pressure cuff up to about 20 millimeters of mercury, which is that lowest number on the dial in the blood pressure cuff, and we're making sure that the cuff doesn't deflate at all, that it's held at a constant pressure. And then it's kind of hard to show because I don't have tons of hands, but maybe.
But you do actually have tons of hands.
I do have tons of hands. I have like 50 with me right now, but I need more of my own hands. But what we're doing, this is Dr. Eric, he's here, he popped in to say hi. And so what we're doing is we're just wrapping the hand around, and then we're actually going to close the hand and measure how the dial will change based on the hand squeezing the cuff. So we've noted our own hands can squeeze the cuff and give a pretty significant rise. We got it to about 140 millimeters of mercury. We tested the smallest hand we have, and it hardly moved the dial at all. I think we got maybe 5 or 6 millimeters, not very much at all. So we'll see probably that the bigger hands have bigger force outputs, and also they're just physically able to wrap around the wrapped blood pressure cuff. And so again, I'm expecting to see a bit of a difference between the sizing of the hands. Anything that seems to be from the 1.3 size up can all exhibit the same sort of motions. They can do the same sort of things. We'll see the same numbers from them, but the smaller hands definitely have a bit more challenging aspects to them in testing. They can't always fit in everything that we're designing. So we're going to keep an eye out on that. But there are a couple of numbers we've got right now. If anyone has advice or has other things they'd like us to do, like I said, the Whipple tube is a great suggestion, and we like that so far. So that's kind of where we're at. We found some more numbers, and we're just going to keep testing and seeing what we have. So I don't know if anybody has questions for us, or...
It's actually kind of interesting because hold on, you echo. If we at Maker Faire last year at the New York Maker Faire, we had OT students with us from a program in New York, and they had set up different sorts of games for people to do with the hands, so tossing bean bags, pulling scarves out of a bag, doing all sorts of like a fishing game. And it's really interesting because we had demo hands of several different hands. We had demo raptors and raptor reloadeds and phoenixes and an osprey as well. And everybody preferred the phoenix. And the OTs would argue, oh, we need to get those phoenixes back because those are the ones that perform those tasks better. So that was actually kind of interesting because you sort of found the same sort of thing. And I think that that's kind of interesting. You've unmute.
One question that we had, sorry, one question that we had was with your design, you said that you only needed 6 newtons of force for the adaptive grip as compared to with the non-adaptive grip. Was this testing between the same hand design? So like, was it the Phoenix with the adaptive was 6 and the Phoenix without the adaptive was a 13? Is that what you found?
We only tested a Raptor Reloaded and then a Phoenix with the adaptive grip. We haven't looked at a Phoenix with the unadaptive grip or just kind of the regular grip yet. What we had right in front of us, we took a ton of our hands to the Maker Faire, so a bunch got strings broken and band snaps, and not everything is like back up and running yet. So what we had Monday morning was the Phoenix with the adaptive grip and just a regular Raptor Reloaded. But I did notice that the Raptor Reloaded, which just has that very kind of all-or-nothing grip to it, really struggled to maintain on objects because a lot of the force was put in to try and get a full grip over it. Whereas when we hold objects every day, you know, when you're holding a coffee cup, I usually only hold it with, you know, maybe 3 fingers, or, you know, 2 fingers and the thumb, really. And so we found that maybe the full grip is kind of hindering some of the motion and the functionality in the hands. So we'll test, we'll see if we can get some of our other Phoenixes ready to go and see what we find between the adaptive grip and just the regular grip. But from what I saw between just the 2 rough versions, even though they were separate versions, there was a significant difference between grip pattern and just functionality and what it was able to do.
Sure, yeah, that's really cool.
So, have you ever tried painting the inside of the hand and then grabbing something and just seeing what the surface area is making contact?
Yeah, we thought about that. I wanted to get my hands on some like easy washable paint, so we had these nicely colored hands. Part of the reason we wanted the Theraputty was to measure some of that, so we're going to measure surface area change, but also just to see in the grip what is actually gripping. And from what we found with the adaptive grip was that it was that first and middle finger were definitely gripping before the pinky and the ring fingers, which is what we can expect. And we found, of course, with them was assisting, but we really found a lot of the grip came from those first 2 fingers. And so that helped us, but we're going to see where the Theraputty goes, but I have that in the back of my mind, and I'd like to see what happens. But yeah, I'll definitely make a star by that and see if we should add that into our list.
Yeah, I was going to say the Theraputty that you were using kind of does some of it, doesn't it?
Mm-hmm. It does, yeah. And it's easy. It's kind of hard to see because it is monotone in its color. It doesn't have a whole lot of variation, so it might be difficult to photograph, but we'll at least make note if we see any changes. But from when we were doing our rough testing of the Theraputty, we did see some differences in the adaptive grip versus the Raptor Reloaded, which just had all of the fingers gripping equally, which has benefits and disadvantages to both sides of it. So. But that's what we're trying to figure out in our research is what is going to be better, what works better. But Justine, I definitely have a preference for the Phoenix hands, and I think I'm falling in line with your OT students from last year. So does anybody else have any questions, or that's all we have for right now? We'll keep you updated with anything else that we come up with or anything else that we find.
Does anybody have anything else? All right, hang on, I'll wrap us up, and then we can wrap up after this. Okay, thank you very much. We'll have the Interns back next for another. You get to sort of peek behind the curtains and see what they're up to. So until then, happy printing. Thanks a lot. Bye-bye.